Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in college mathematics, you're in the right spot, so go ahead and click the subscribe button. That said, let's get into the current video. I'm going to talk about the limit of a recursive sequence. In other words, if I give you a recursive sequence, how do I find what it converges to? Start with an example. So let's say I give you the following recursive sequence. I'm going to give you the first term, and the first term is going to be, let's see if I get a little more ink in there. Turn that down a little bit, didn't I? The first term of the sequence, let's say, is 8. And then let's say the recurrence relation, an plus 1. What I do is I'm going to take the previous term, and then I'm going to divide it by 2. Okay? Well, let's write out the terms of the sequence. A1, of course, is given to be 8. A2, well, this is where we use the recurrence relation, right? So in order to generate the next term, I have to use this formula. So a sub 2 would be a1 divided by 2. a1 was 8, so this is 8 divided by 2, which is 4. All right, a3. This is the previous term divided by 2. Previous term was 4. 4 divided by 2 is 2. a4 would be the previous term divided by 2. 2 over 2, which is 1. Let's do a couple more terms, kind of get an idea of what's happening to these successive terms. A5 would be A4 divided by 2, which is 1 over 2. A6 would be A5 over 2, which is a half over 2, which is equal to 1/4. Now, let's go ahead and let's write the terms just sort of in one row here. So we have 8, 4, 2, 1, a half, and a quarter. And of course it keeps going. Now the question is, does the sequence converge, and what does it converge to? Well, we could see that if we the idea is I keep cutting it in half. So we could see that the next one would be, I cut a quarter in half, so I get an 1/8 and then a 1/16 and so on and so forth. And it looks that these terms are converging to 0. So again, that's just an educated guess here. That's not a proof. That's not a formal computation, right? That's not something that we can just say, well, it looks like it's going to 0, therefore it's going to 0. Spoiler alert, it is going to 0. But we want to be able to formally justify this. And let me turn the lights up just a little bit. Okay. So let's see if we can formally justify this. All right. Now, these are the terms in the sequence a sub n. So let me just kind of list this. This is the terms for the sequence a sub n. So this is when n is 1, n is 2, n is 3, so on and so forth. What I want to do is let's look at a related sequence that I'm going to title an plus 1. Again, off to the side here or directly below this, this is when n is equal to 1, and this is n is equal to 2, and n is equal to 3, so on and so forth. Hopefully you can see that. Now, if I wanted to take that same expression and I was going to use an plus 1, well, this would be, again, when n is 1, n is 2, n is 3, so on and so forth. Well, when n is 1, this would be a sub 2, which is 4. And then when n is 2, that'd be a3, which is 2. Oops, let me put it over here. Let me line it up here. When n is 3, that'd be a sub 4, which is 1. And you can see that an plus 1 is simply this sequence I just started here. So in other words, this sequence, an plus 1, would be 4, 2, 1, a half, a quarter, etc. Now again, that looks like it's converging to 0, which it is, but in order to formally justify that, here's how we're going to do it. I'm going to go back to this one, and I'm going to say it converges to some number, right? And this is the exact same list starting here. So whatever this converges to, this has to converge to the same thing. So I'm going to say this converges to L as well. That's going to be my starting point. Now, here's how we actually formally show that this converges to 0. I'm going to start it as follows. L is equal to the limit as n approaches infinity of a sub n. So that's what, when we find the limit of a sequence, we take the limit at infinity, and we're saying that this converges to L. Well, looking at these two lines right here, we can see that an converges to L. Well, so does an plus 1. So this is also equal to the limit as n approaches infinity of an plus 1. But here's where we're going to use the recurrence relation. We know the relationship between an plus 1 and an. So this limit, since this expression is equal to this expression, I can write this as the limit as n approaches infinity of an over 2. But remember, we said that an, this sequence, converges to L. Therefore, an over 2 converges to L over 2. Now we have to solve the following equation. Let me put it up here just so I can have everything on the board. We now have the equation L is equal to L over 2. Of course, we could solve this a variety of ways. If I subtract 1/2 L from both sides, then I would get 1/2 L is equal to 0, and then multiply by 2, I get, as expected, the limit value is 0. Okay, now for this particular example, we had a really good idea of what these terms were converging to. You know, at this point in your Calc 2 course, assuming you're in Calc 2, you can kind of see the progression of these terms, and it just seems very, very reasonable that it's going to approach the number 0. Well, let's do a second example where it's not at all clear what it's converging to, and we'll go ahead and we'll use the same method, and we'll find the limit of the sequence. So let me clean this up and set up another example. Okay. This time, let's say the first term of the sequence is, let's say, 2. Okay, so the first term of the sequence is 2. And then here's my recurrence relation. I'm going to say an plus 1 is given by the following. I'm going to take the square root of 2 plus the previous term. Okay, so this recurrence relation is a little bit more complicated than the previous one. So I take 2 plus the previous term, and then I take the square root of that. Let's do two things. Let's write out the first couple of terms and then see if we can kind of get any sort of sense as to what it's converging to. And then we'll go ahead and we'll use the formal method to find out what it actually converges to. All right, well, let's see. A1, of course, is 2. A2 would be the square root of 2 plus the previous term, which is equal to the square root of 2 plus 2, which is 4. Of course, then that is 2. A sub 3. All right, I don't like this. I just made this one up. Of course, this one is just going to be the constant sequence, 2, 2, 2, 2. Let me go back. Let me adjust this. Let's say the first term of the sequence is 3. All right. Now this one will work the way I want it to. Let's say a sub 1 is going to be given by, of course, 3, and then a sub 2 is the square root of 2 plus the previous term. So 2 plus 3, so therefore this would be the square root of 5. And then a3 is going to be the square root of 2 plus the previous term, which is the square root of 2 plus the square root of 5. And then a4, again, is the square root of 2 plus the previous term, which is the square root of 2 plus, now remember the previous term is this, so therefore I'm going to stick this right here, so the square root of 2 plus the square root of 5. And you can see essentially that what's happening is each successive term here, this is just getting embedded into this radical. So we come up with this sequence of nested radicals. And let's see, let me clean this up and let's kind of take a look at that and see if we have any indication as to what this could be converging to. Well, I think maybe it's reasonable that whatever it converges to is somehow related to a square root. Maybe there's a 2 in there. You know, it's kind of hard to tell, right? Compared to the previous one that it was clearly converging to 0. Well, we don't need to use any sort of intuition here, like, oh, well, it converges to 1 plus the square root of 7. Who knows what it converges to? We can use the previous method and formally do it, right? We're going to say L is equal to whatever the sequence converges to. So the limit as n approaches infinity of a sub n. Well, remember that the sequence a n plus 1 is just one term later, so therefore it converges to the same thing, and therefore this is equal to the limit as n approaches infinity of a n plus 1. Just like the previous example, now I'm going to use the recurrence relation, and I'm going to say this is the limit as n approaches infinity of the square root of 2 plus a n. Now this is where we use a property of limits, that the square root is a continuous function, so the limit and the square root we can interchange. So the limit of the square root is the square root of the limit, and then if I take the limit of a constant, I get that constant, and of course the limit of a n, as we said, was L. So that gives me the following equation. L is equal to the square root of 2 plus L. Okay, and now we have to solve this. All right, so let's go ahead, square both sides. I get L squared is equal to 2 plus L, and I'm kind of shift it over here so I can have like 2 different columns. Then I would have L squared minus L minus 2 equals 0, and so we just have to solve a quadratic equation. This one doesn't look like it factors nicely, so therefore let's just use the quadratic formula. So therefore the value of L is given by, so it's negative b, so that'd be negative 1 plus or minus the square root of b squared minus 4ac all over 2a. Okay, clean that up. I get L is equal to 1 plus or minus the square root. So negative 1 squared is 1, and then 4 and negative 2, that would give me 8. So this would be plus or minus the square root of 9 all over 2. So I get 1 plus or minus 3 over 2, which is 1. So I get 4 over 2, which is 2. And 1 minus 3 is negative 2 over 2 is negative 1. Well, I guess that did factor nicely. I guess I was just assuming. Oh well. At home you're probably thinking, well, of course that factored nicely. What was he thinking? So product, of course, is negative 2. Sum is, yeah, sorry. So this would factor as L minus 2, L plus 1, right? Product is negative 2. Sum is negative 1. Anyway, okay, so that one did factor nicely. Just generally they don't, so I was just kind of assuming that they wouldn't, but without even really looking at it. Anyway, we get 2 and negative 1. Here's the idea. A limit, if it exists, is unique. So if this limit exists, it has one value. The limit is this number or this number. I can't get progressively closer to 4 and progressively closer to negative 3, right? It gets progressively closer to one number. So therefore, the limit is one of these two. Well, we can quickly narrow it down because these are all positive numbers, and therefore it has to be this one. So therefore, this sequence of radicals actually converges to 2. Thank you for watching. Please consider subscribing.